Collective Intelligence in AI, the Introduction of AB-MCTS. Overview. On July 1, 2025, Sakana AI announced a groundbreaking algorithm, the Adaptive Branching Monte Carlo Tree Search AB-MCTS, aimed at enhancing the capabilities of artificial intelligence AI through collective intelligence. This new inference time scaling algorithm allows various advanced AI models such as Gemini 2.5 Pro 04 Mini and DeepSeek R1-0528 to collaborate and leverage their unique strengths to solve complex problems more effectively than individual models. Inspired by human collective intelligence, the algorithm embodies the principle that diverse perspectives and expertise can lead to superior problem-solving outcomes. Inspiration and background. The idea of collective intelligence is rooted in the understanding that collaboration among individuals often yields greater achievements than solitary efforts. Historical milestones such as the Apollo program and the Human Genome Project exemplify how diverse teams can surmount technological challenges. Sakana AI translates this concept into the realm of AI, positing that frontier models like ChatGPT, Gemini, and DeepSeek, each with distinct characteristics shaped by their training data, can synergistically address problems that are difficult for any single model to tackle. Previously in 2024, Sakana AI researched evolutionary model merging, focusing on mixing to create new models. The advent of AB-MCTS represents a paradigm shift towards mixing to use existing powerful models during inference. This shift emphasizes the value of collaboration among existing models during problem solving rather than creating entirely new models. The AB-MCTS algorithm. AB-MCTS enables AI models to engage in trial and error processes akin to human problem solving. The algorithm's design facilitates a balance between depth and width in search strategies, utilizing a Monte Carlo Tree Search framework augmented with Thompson Sampling. This allows the algorithm to decide whether to refine existing solutions or generate new ones. The initial results on the ARC-AGI-2 benchmark indicate that the combination of 04 Mini, Gemini 2.5 Pro, and DeepSeek R1-0528 significantly outperforms individual models, showcasing the potential of collective intelligence in enhancing AI performance. Key features of AB-MCTS include: 1. Trial and error efficiency, the ability to refine answers through repeated attempts or explore new solutions based on previous results, mimics human-like problem solving. 2. Integration of multiple models, the flexible architecture allows for the combination of different models, enhancing problem-solving capabilities, especially for tasks requiring varied expertise. 3. Dynamic search strategies. The algorithm adapts its search strategy based on the problem context, improving the potential for discovering optimal solutions. Multi-LLM AB-MCTS, expanding the horizons. Building upon the success of AB-MCTS, Sakana AI introduced the Multi-LLM AB-MCTS, which allows for adaptive exploration not just of search directions but also the selection of the most effective model for particular problems. This method dynamically allocates tasks to models based on their strengths, significantly improving the success rate for complex tasks that previously challenged individual AIs. Experimental results revealed that this collaborative framework increased the success rate to over 30% on the ARC-AGI-2 benchmark. Highlights of the Multi-LLM AB-MCTS include: enhanced problem solving. The combination of multiple models allows for addressing a broader range of problems, leveraging the strengths of each model for specific tasks. Adaptive model selection. The system dynamically learns which models perform best for particular problems, leading to improved outcomes through targeted collaboration. Trial and error dynamics. By combining the strengths of multiple AIs, Multi-LLM AB-MCTS can refine solutions iteratively, pushing the boundaries of what is achievable through collective intelligence. Key findings and performance metrics. The initial findings from the implementation of AB-MCTS and Multi-LLM AB-MCTS on the ARC-AGI-2 benchmark were promising. 1. Integration of multiple models. The framework demonstrated that combining different models significantly enhances problem-solving capabilities. 2. Improved success rates. The PASS at 250 metric showed that the collaborative model outperformed traditional methods, achieving better success rates in problem solving. 3. Diverse strengths utilization. The ability of the algorithm to dynamically allocate tasks based on model strengths was key to its success. Conclusion and future directions. The introduction of AB-MCTS marks a significant advancement in leveraging collective intelligence for AI problem solving. By allowing multiple frontier models to cooperate, Sakana AI has opened new avenues for addressing complex challenges in a manner reminiscent of collaborative human efforts. The initial success of the algorithm on the ARC-AGI-2 benchmark underscores its potential to revolutionize AI performance through collective intelligence. Moving forward, Sakana AI is committed to refining the final answer selection processes and improving reward models to enhance the effectiveness of Multi-LLM AB-MCTS. The ongoing research aims to further unlock the potential of inference time scaling methodologies, paving the way for AI systems that collaboratively tackle increasingly complex problems. Timeline of events. 2024, Sakana AI conducts pioneering research on evolutionary model merging. July 1, 2025, the announcement of AB-MCTS and initial results showcasing its effectiveness on the ARC-AGI-2 benchmark. References. For those interested in exploring this groundbreaking research further, the following resources are available. Blog, Sakana AI AB-MCTS, https://sakana.ai/ab-MCTS. Research paper, wider or deeper? Scaling LLM inference time compute with adaptive branching tree search //arcsib.org/abs/2503.04412. Algorithm implementation, TreeQuest on github//github.com/sakanaai/TreeQuest. ARC-AGI-2 experiment code, AB-MCTS on github//github.com/sakanaai/ab-MCTS ARC-2. Sakana AI's innovative approach demonstrates the potential of harnessing collective intelligence in AI, paving the way for future developments in the field. The content discusses a new algorithm developed by Sakana AI called AB-MCTS Adaptive Branching Monte Carlo Tree Search, which enables multiple AI models to collaborate and enhance their problem-solving capabilities through collective intelligence. Here are some counterintuitive insights from the content. 1. Collaboration over competition. It is commonly believed that AI models should be optimized individually to achieve the best performance. However, the AB-MCTS algorithm suggests that collaboration among multiple models can yield better results. This counters the intuition that singular optimization leads to the best outcomes. 2. Utilizing biases as strengths. AI models are often seen as limited by their unique biases and strengths derived from their training data. The AB-MCTS approach turns this notion on its head by viewing these differences as valuable resources for collective problem-solving rather than obstacles. 3. Trial and error as a methodology. Traditionally, AI systems are viewed as systematic and deterministic, often focusing on finding the best solution without revisiting previous attempts. The AB-MCTS algorithm's emphasis on trial and error mimics human-like problem-solving, challenging the notion that AI should function purely through linear logical processes. 4. Performance gains from exploration. The content indicates that allowing models to explore both depth refinement and width new solutions can lead to better results. This dual approach can be counterintuitive, as it suggests that sometimes generating new solutions exploration can be more beneficial than simply refining existing ones. 5. Dynamic allocation of tasks. The idea that a single model can excel in certain areas while struggling in others can lead to the assumption that a model's performance is fixed. However, the Multi-LLM AB-MCTS algorithm highlights that by dynamically selecting the most effective model for specific tasks, AI can adapt and improve performance significantly. 6. Success from combining weaknesses. It challenges the conventional wisdom that only the strongest models should be utilized. The content illustrates that models which may not perform well individually can contribute positively when combined in a collaborative framework, leading to solutions that no single model could achieve alone. 7. Increased computational resources. While it is generally understood that adding more computational resources can improve performance, AB-MCTS suggests that the method of utilizing these resources, i.e. through collective intelligence, is just as crucial, if not more so, than the resources themselves. 8. The threshold of success. The initial experiments showed that the collaborative model could outperform individual models significantly. This suggests that the threshold for success in challenging benchmarks can be altered when leveraging collective intelligence, which is not typically anticipated in traditional AI development approaches. These counterintuitive insights indicate a shift in how AI can be developed and applied, moving away from the focus on individual excellence to embracing collaboration and the strengths found in diversity among models. Sakana AI's introduction of the adaptive branching Monte Carlo Tree Search AB-MCTS algorithm marks a significant advancement in artificial intelligence, particularly in the realm of collective intelligence. While the core concepts and initial results of this algorithm are likely to capture the attention of many readers, several nuances and implications within the report merit closer examination. These overlooked details provide invaluable insights into the potential future of AI collaboration. 1. The shift from mixing to create to mixing to use. One of the most critical yet subtle shifts in Sakana AI's approach is the transition from mixing models to create new ones to utilizing existing models collaboratively. This distinction is crucial as it reflects a fundamental change in how AI systems can be developed and deployed. By focusing on existing frontier models, each with unique strengths and training biases, AB-MCTS leverages the current capabilities of AI rather than attempting to reinvent the wheel. This not only saves resources but also accelerates the pace of innovation by allowing multiple models to contribute their strengths in real time. Significance: this approach can lead to faster problem-solving capabilities, as it reduces the time and resources typically spent on training new models from scratch. It emphasizes the potential of collaboration over competition in AI development, suggesting that future advancements could increasingly rely on cooperative strategies rather than isolated innovations. 2. Trial and error efficiency. The report highlights the ability of AB-MCTS to facilitate a trial and error process akin to human problem solving. While many understand the basic premise of trial and error in AI, the report underscores how this method can be dramatically enhanced through collaborative interactions between models. By allowing different models to refine and build upon each other's outputs, the search for solutions becomes more dynamic and effective. Significance: the implication of this is profound. It suggests that AI could reach new levels of sophistication in reasoning and problem solving. The ability for models to not only work independently but also iteratively improve upon each other's suggestions mimics human teamwork in solving complex issues, potentially leading to breakthroughs in areas that were previously deemed too challenging for AI. 3. Balancing depth and width in search strategies. The algorithm's ability to balance depth, refining existing solutions, and width, generating new solutions through the Monte Carlo Tree Search framework, is a sophisticated enhancement that many may overlook. This dual approach allows for more nuanced decision-making about which path to pursue depending on the context and the problem at hand. Significance: this flexibility in search strategy could allow AI systems to adapt more readily to various challenges, improving their overall performance. It also suggests a new paradigm for algorithm development where adaptability becomes a core feature, potentially transforming how AI strategies are formulated and executed. 4. Dynamic model selection in Multi-LLM AB-MCTS. The introduction of Multi-LLM AB-MCTS, which selects the most effective model for specific problems, is a pivotal advancement that can be easily underestimated. This dynamic allocation of tasks based on model strengths showcases an advanced level of operational intelligence within the algorithm. Significance: this capability not only enhances performance but also makes the system more efficient. Understanding which model excels at what task allows for optimized resource use, reducing unnecessary computations. This indicates a future where AI could operate in a more human-like manner. Choosing the right team member for the job at hand based on situational analysis. 5. Potential for collective intelligence beyond AI. While the report is primarily focused on AI, the principles underlying AB-MCTS could have broader implications for collaborative problem-solving across various domains. The algorithm's design, rooted in collective intelligence, suggests that similar methodologies could be applied to human teams or organizations, enhancing how diverse groups work together to solve complex challenges. Significance: this cross-disciplinary application could spark interest in collaborative frameworks that leverage the strengths of different entities, human or machine, working together. The success of AB-MCTS might encourage others to explore collective intelligence in different contexts, potentially leading to innovations in teamwork and problem-solving strategies beyond AI. 6. Implications for future AI research and development. The report points out that the ongoing research and development efforts will focus on refining the final answer selection processes and improving reward models. This highlights an important aspect of AI development: the continuous evolution of methodologies to enhance performance. Significance: the iterative nature of this research emphasizes the importance of feedback loops in AI development, where each iteration builds upon prior findings. This could lead to an accelerating cycle of improvement where newer models and algorithms emerge faster as a result of collaborative frameworks like AB-MCTS. 7. Broader impact on benchmarking and evaluation metrics. The use of ARC-AGI-2 as a benchmark for testing the efficacy of AB-MCTS is noteworthy. The report discusses how this benchmark provides a platform for evaluating human-like reasoning and problem-solving capabilities, which could redefine how AI performance is assessed. Significance: as benchmarks evolve to reflect more complex cognitive tasks, the metrics for evaluating AI will also need to adapt. The success of AB-MCTS on such benchmarks could influence future research directions, where more emphasis is placed on collaborative and adaptable AI systems rather than isolated performance metrics. Conclusion: Sakana AI's AB-MCTS algorithm marks a transformative step in harnessing collective intelligence within AI. The nuances embedded within the report, such as the shift to collaborative utilization of existing models, the efficiency of trial-and-error processes, and the dynamic selection of models, underscore the algorithm's potential to revolutionize problem-solving capabilities. By acknowledging these overlooked details, stakeholders in the AI field can better appreciate the significance of this work and its implications for future advancements in AI collaboration and development. 1. Collective intelligence in AI. The core concept of leveraging collective intelligence inspired by human collaboration is pivotal in enhancing AI capabilities. Sakana AI's AB-MCTS algorithm embodies this principle by allowing multiple advanced AI models, like Gemini 2.5 Pro 04 Mini and DeepSeek R1-0528, to work together synergistically. Each model possesses unique strengths and biases, which when combined provide a rich resource for solving complex problems that any single AI might struggle with. This approach suggests that future advancements in AI may increasingly rely on collaborative frameworks similar to team dynamics in human problem solving. 2. AB-MCTS and Multi-LLM AB-MCTS. The AB-MCTS algorithm allows for an innovative trial-and-error method tailored for AI models, enhancing their problem-solving capacities. By balancing depth and width in its search strategies, AB-MCTS employs a Monte Carlo Tree Search framework augmented with Thompson Sampling, enabling models to adaptively search for optimal solutions. The subsequent Multi-LLM AB-MCTS expands on this by not only selecting the best search strategy but also dynamically allocating tasks to the most suitable models based on their strengths. This dual-layered approach demonstrates a significant leap in AI's capability to tackle complex tasks that previously stumped individual models, achieving success rates above 30% on the challenging ARC-AGI-2 benchmark. 3. Initial results and performance metrics. The initial results from testing AB-MCTS and Multi-LLM AB-MCTS on the ARC-AGI-2 benchmark are promising, showcasing a significant performance improvement over traditional problem-solving methods. The collaborative model outperformed individual models by a considerable margin, with the pass at 250 success rate indicating that the collective approach is effective. This metric highlights the potential of combining multiple LLMs large language models to enhance overall AI performance, thus setting a new standard for evaluating AI capabilities on complex tasks. For future directions and implications for AI research, the research outlines a path forward for AI development, emphasizing the importance of scaling inference time processes through collective intelligence. Sakana AI's work, which shifts from merely creating new models to utilizing existing ones in collaborative frameworks, opens new avenues for research in AI. Future efforts will likely focus on refining selection algorithms and reward models, which could further enhance the effectiveness of Multi-LLM AB-MCTS. This shift signifies a broader trend in AI research toward leveraging established models in innovative ways, promoting a collaborative approach similar to human expert teams, and potentially redefining benchmarks for success in AI problem solving. 1. The Manhattan Project 1942 to 1946. The Manhattan Project was a collaborative effort during World War II involving scientists, engineers, and military personnel from the United States, the United Kingdom, and Canada to develop the first nuclear weapons. Notable figures such as J. Robert Oppenheimer, Enrico Fermi, and Richard Feynman were part of this project, which exemplified the power of collective intelligence in solving complex scientific challenges. The successful detonation of atomic bombs in 1945 demonstrated the effectiveness of pooling diverse expertise and resources in a high-stakes environment. 2. The Apollo 11 mission 1969. The Apollo 11 mission was a landmark achievement in space exploration, marking the first time humans landed on the moon. This monumental task required the collaboration of thousands of individuals across NASA and its contractors, showcasing the importance of collective intelligence. Engineers, scientists, mathematicians, and astronauts, including Neil Armstrong and Buzz Aldrin, worked in tandem to overcome numerous technological and logistical challenges. The success of Apollo 11 highlighted how diverse skills and knowledge could converge to achieve extraordinary goals. 3. The Human Genome Project 1990 to 2003. Launched in 1990, the Human Genome Project was an international scientific research initiative aimed at mapping and understanding all the genes of the human species. This ambitious endeavor involved collaboration among scientists from various countries and disciplines, including genetics, bioinformatics, and ethics. The project's completion in 2003 provided a comprehensive reference for human DNA, paving the way for advances in medicine and biotechnology. It exemplified how collective intelligence in the scientific community could lead to groundbreaking discoveries that have lasting impacts on health and human understanding. The future of AI, particularly in the context of collective intelligence and inference time scaling through algorithms like adaptive branching, Monte Carlo Tree Search AB-MCTS, is poised for transformative advancements. As we look ahead, several predictions can be drawn based on the current trajectory of AI development and the principles underlying collective intelligence. 1. Enhanced collaboration among AI models. The success of AB-MCTS demonstrates that AI models can leverage their unique strengths by collaborating rather than functioning in isolation. We can expect future AI architectures to increasingly embrace multi-agent systems where diverse models, each with its own expertise, work together seamlessly to tackle complex problems. This will likely lead to more sophisticated solutions that surpass the capabilities of any single model. 2. Evolution of problem-solving approaches. As AB-MCTS highlights the efficacy of trial and error in problem-solving, we predict that AI will adopt more human-like reasoning processes. Future models will not only perform deep analyses but will also iterate upon prior attempts, refining their outputs based on feedback and previous results. This dynamic approach may evolve further, incorporating real-time learning mechanisms that adapt based on user interactions and environmental changes. 3. Increased application across domains. The collective intelligence demonstrated by AB-MCTS opens avenues for AI applications across various fields. From healthcare diagnostics, where diverse models can analyze medical data collaboratively, to creative industries where multiple AIs contribute unique perspectives on artistic projects, we foresee a surge in interdisciplinary applications. AI's ability to collaborate will enhance its utility in solving multifaceted challenges in fields like climate science, education, and engineering. 4. Democratization of AI capabilities. As collective intelligence algorithms like AB-MCTS are made publicly accessible, such as through platforms like TreeQuest, we anticipate a democratization of AI capabilities. Smaller organizations and individuals will gain access to sophisticated AI tools that enable them to solve problems that were previously out of reach. This democratization could lead to a surge in innovation as more diverse voices contribute to AI development. 5. Ethical and governance considerations. As AI systems become more collaborative and powerful, ethical considerations will become paramount. There will be an increasing need for frameworks that govern the interactions between AI models, ensuring that their collective outputs align with societal values and ethical standards. We can expect the emergence of new regulations and best practices aimed at ensuring transparency, accountability, and fairness in AI collaborations. 6. Continuous learning and adaptation. The future of AI will likely involve models that are not only trained on vast datasets but also continuously learn from new data inputs and experiences. This will be particularly important in dynamic environments where the context of problems shifts rapidly. AI systems that can adapt and learn in real time will outperform static models, making them invaluable in areas like finance, security, and customer service. 7. Integration of human-AI collaboration. With the rise of collective intelligence in AI, we foresee a future where human experts and AI systems work in tandem. Rather than replacing human decision-makers, AI will serve as a collaborative partner, augmenting human abilities and providing insights that enhance decision-making. This symbiotic relationship may redefine job roles, with humans focusing on strategic oversight while AI handles complex computations and data analysis. 8. Advancements in cognitive architectures. The principles of collective intelligence and adaptive search strategies are likely to inspire new cognitive architectures for AI. Future models may incorporate elements of human cognition such as reasoning, creativity, and emotional intelligence, leading to more intuitive interactions between AI and users. This could transform user experiences, making AI tools more relatable and effective in addressing human needs. 9. Performance metrics and evaluation. As collective AI systems become more prevalent, the metrics used to evaluate their performance will also evolve. Traditional benchmarks may be supplemented or replaced by metrics that account for the collaborative nature of these systems. New evaluation frameworks will be necessary to assess not only the accuracy of outputs but also the efficiency and effectiveness of collaborative processes among multiple AI models. 10. Global collaboration and research. Finally, the future of AI will likely see increased global collaboration among researchers and practitioners. The sharing of findings, models, and methodologies will facilitate the rapid advancement of collective intelligence approaches. International partnerships could lead to breakthroughs in AI capabilities with a focus on addressing global challenges such as pandemics, climate change, and inequality. In conclusion, the future of AI, particularly through frameworks like AB-MCTS, promises to be increasingly collaborative, adaptive, and integrated into human processes. As we harness the power of collective intelligence, the potential for solving complex problems will expand, leading to a more innovative and equitable future for all.